Probably I simply forgot some detail, and this is too ambitious to formulate the theorem. Well, this way it doesn't work. Okay, let's erase this. No, I'm not going to prove this. Something additional is required to have such a theorem. Well, let's still consider this left regular representation. Okay. Because here the Zohr lemma is not applicable probably, and so it's a little harder for me to state such a theorem. So let's consider, well, forget it. We consider the right regular representation T ut of a compact group G. Well, and okay, we want to do something with its invariant subspaces. Well, so lemma each invariant subspace for this representation contains a non-zero finite dimensional invariant subspace. Contains a non-zero finite dimensional invariant subspace. Why so? This follows from the Peter-Weil theorem. Okay. Each again here non-zero, because otherwise it would be incorrect, of course. So proof. Consider an invariant subspace K at non-zero. Since it is non-zero, well, there are non-zero functions there, and okay, so there is a function k in K which is not zero, and h here is L2. Sorry, h here is L2, sure. L2. H here is L2. So there is a non-zero function there, and since it's non-zero, it must have a non-zero scalar product with some continuous finite dimensional function. Even we may assume, no, probably let it be so. Or even let me write it in this way: integral over g f h is not equal to 0, because the set of such functions is dense in L2 and also in C on G, so we may write it in this way without bar here. I don't want to have a scalar product here. And now again consider consider the operator th, and this th of k is equal to the integral over g of k of at the point s, k of su st minus 1 to the power minus 1 h of t dt. Okay. Now my function is in k, so all these functions are also in k. All the shifts are also in k, right shifts. And here we have a continuous function. So this integral, if we approximate it by Riemann sums or something like that, so we see that this is somehow some infinite linear combinations of functions in the space k. So this is in k, and if we replace this integral by some Riemann sum, we see that the result will be in k. And this Riemann sums approximate this uniformly. Again, we should use some form continuity here. So this is continuous. This is continuous. So if you approximate it by Riemann sums, then we obtain something in k. So what does this mean? This means that this is also in k. If we integrate something in k with a continuous function, we obtain also something in k. So this function lies in k. It is non-zero because it is non-zero. Okay. Let me correct probably. This condition, probably it is better to write it in this form: integral over g of k of t to the power minus 1 h of t dt is not equal to 0. Because if this function is non-zero, then this function is also non-zero, and its integral with some function, some finite dimensional function, also should be non-zero. So, so this function is non-zero because it is continuous. It is continuous. Th of k is continuous. We saw it already that this function is also continuous. And it is non-zero at the point E. At the point, if I put S equal to the unity of our group, then I obtain that Th of k, Th of k is not zero because of this relation. So this is non-zero function. And we have already seen that this is finite dimensional because, again, if we replace here S by SU and T, how? Let's replace here S by SU, THK of SU is equal to the integral over G of K S U T to the power minus 1 H of T dt. And what should I do here? I should introduce a new variable, say v, so that v to the power minus 1 be equal to, if you replace t by tu here, then this will not influence the integral, and we obtain the integral over g of k of s h of t u dt f no tu t to the power minus 1 s t to the power minus 1. Okay. So we obtain again the formula which we have already used, that is that T H of K shift by U is equal to TH of KU. Well, and precisely as we did this in the proof of the preceding statement, we see that this element is finite dimensional. This thing is finite dimensional. We have already done this, but I remind you how this is done. Simply, we use the fact that K is finite dimensional, H is finite dimensional, well, TH sorry, no, not this thing. Well, who is who? Who is who here? So K is in K, H is something continuous, H is something continuous. Well, not quite, not this. So we use this formula. And use the fact that H is finite dimensional. And we prove that this is finite dimensional. And to do this, we use this representation of the shift of THK and let HU1 and so on, HUN be a basis in the linear span of HS, where HU, where U runs over G. So then this guy is represented as the sum of over I from 1 to n, alpha I, H UI, okay, and this shows that so surely this alpha I depends on U. But this is not interesting right now. The sum of alpha I for I from 1 to n, the integral over G of K S T to the power minus 1 H let's write HU H of T. So HU is represented in this way. Then we write this formula, and this means that, okay, so this implies that THKU is a linear combination of THKU eta UI. So we write this, and we again use this initial formula, but this time with ui instead of u, and we obtain the function th shifted by ui here. So it follows that for every u, this function is a linear combination of a finite number of shifts of this function, so it is finite dimensional. Okay? Well, okay. So we have proved the lemma. Each non-zero invariant subspace for this representation contains a non-zero finite dimensional invariant subspace. So this finite dimensional invariant subspace will be simply the subspace generated by this function t h of k. So our subspace in question the subspace we look for is the linear half of the shifts of some continuous finite dimensional function. Specifically, this will be this function thk. Okay, so every invariant subspace has a finite dimensional invariant subspace, and this subspace is generated by a finite dimensional function. Well, such spaces generated by one function are called cyclic. Well, definition. Cyclic the cyclic subspace of L2 of G generated by a function G in L2 is by definition the closed linear hull of all shifts of G. So this finite dimensional subspace is cyclic. It is in fact generated by the shifts of one function, of some finite dimensional function which is also non-zero. And now, when we know this, we really can apply the third lemma. theorem. There is a decomposition of L2 of G into an orthogonal sum of irreducible subspaces of its right regular representation. Its right regular representation. All the subspaces are finite dimensional. Are finite dimensional. Well, and here the Zorn lemma works quite smoothly, not in the incorrect way I wanted to apply it in the general setting. So the proof goes as follows. Consider the collection, say A. This is a collection of all sets A of finite dimensional mutually well, finite dimensional subspaces. Simply, I will list this as one of the properties. Finite dimensional subspaces of L2 of G with the following properties. So first, all subspaces in A are mutually orthogonal. And non-zero. And non-zero. And second, all of them in A are invariant. Under right shifts, under all right shifts. Okay, and let's order this collection, the set A by inclusion. If A1 and A2 are two such collections in calligraphic A, then A1 is greater than A2 means simply that A1 has more subspaces than L2. Every subspace of the collection L2 is a subspace of the collection A1. So we can view this sets A simply as orthogonal decompositions of something into finite dimensional subspaces. Okay. So here really every chain of these spaces has a majorant. Simply the union of this chain is a majorant. And thus A contains a maximal element. Contains a maximal element maximal element B. Consider the orthogonal sum of all E belonging to this maximal element, of all members of this maximal element. So let it be L. Now L is invariant under all right shifts. Hence, its orthogonal complement is also invariant under all right shifts because, all of them are unitary operators, and I explained that the unitary representation, if some space is invariant under it, then the orthogonal complement is also invariant under it. If L orthogonal is not equal to 0, then by the lemma it contains a finite dimensional invariance of space. Okay, this means that then L is not maximal. So it follows that this orthogonal complement must be equal to 0, and thus L2 of G is the orthogonal sum of all elements of B. Okay, so we have split our space L2 of G into an infinite orthogonal sum of some finite dimensional invariance of spaces. They are not irreducible at the moment, but this is already not difficult to make them irreducible because, well, even so now let E be a subspace of L2 of G invariant under all right shifts and finite dimensional. Maybe it is irreducible, maybe not. If it is not irreducible, we can find some small invariant subspace of it. Okay, so let E1 be an invariant subspace of E of smallest possible dimension. So if we have a proper subspace of E which is still invariant, then its dimension is smaller than that of E, okay, we can find a subspace of the smallest possible dimension, which is still invariant, and clearly then E1 is irreducible. It cannot have proper subspaces that are still invariant, because otherwise this dimension wouldn't be minimal. Well, as I already told, then the orthogonal difference of E minus E1 is also invariant. And okay, we can find an irreducible subspace here. Let E2 be an irreducible subspace. So for it, again, we can take an invariant subspace of this one of smallest dimension, and so on, and so on, and so on, and so on. And it's clear that the procedure will stop at some point, because the dimension of the initial space is finite. So at some point we will exhaust our space E. So we have proved the theorem, because first we decomposed our space L2 into a direct sum of finite dimensional invariant subspaces, and then we saw that each of these finite dimensional subspaces splits into an orthogonal sum of irreducible subspaces. So the theorem is proved. Now, what's about these irreducible subspaces? Well, first, so fact. All finite dimensional irreducible subspaces mentioned in the theorem are cyclic and consist of continuous functions. Why are they cyclic? This is a property of every reducible subspace. If we take any element in this irreducible subspace and consider the cyclic subspace corresponding to this element, simply the span of all shifts, the closed linear span of all shifts of this element, then we obtain a non-trivial invariant subspace, which must coincide with our irreducible subspace because it's irreducible. It cannot contain something smaller. Okay? So proof the property of being cyclic is obvious. So consider an irreducible subspace and the invariant, take an element in this space and generate the cyclic subspace with this element. The closed linear span of all shifts of this element, surely it is an invariant subspace, surely it is contained in E, and it is non-trivial, and then it must coincide with E because E is irreducible. So it is cyclic, and simply cyclic by using an arbitrary, it's non-zero element. And why does it consist from continuous functions? We have already proved that such a subspace contains a continuous function. Simply, even a finite dimensional continuous function. So every invariant subspace has a finite dimensional continuous function. And okay, then it must coincide with the cyclic subspace generated by this continuous function. And the cyclic subspace is finite dimensional. It is a linear combination. It is a set of linear combinations of a finite number of shifts of this continuous function. So the entire space E consists of continuous functions. Okay. Now, how does our representation act in this decomposition. Okay. So what do we have? We have the decomposition of L2 of G into the orthogonal sum over alpha of some spaces H alpha, where H alpha for every alpha is finite dimensional. Invariant under all shifts, invariant and irreducible. And all its elements are continuous functions. Okay, this is an orthogonal decomposition, and in each space alpha, in H alpha, we can find an orthogonal basis. How do I denote this in my notes? Let this collection be an orthogonal basis in H alpha. Then, our shifts, our representation UT. So these operators, they act separately on each space H alpha, and they remain unitary there. So simply they have some matrix. If we apply this U to xj alpha, we obtain UT, the sum of some coefficients, which will depend say C. They will depend on T, of course. C of T, and here it will be K Cjk x alpha K, this way. So each shift by T is a unitary operator in each space H alpha, and it acquires a matrix there. It acquires a matrix there. So it acts here in a very simple way, simply as a unitary operator with this matrix. I want to explain you that in the commutative case, the situation is very, very simple. In fact, we know it, but it is instructive to approach it with this side, from this side. So theorem, if G is compact abelian, then all these irreducible spaces are one-dimensional. Moreover, each of them is a linear span of some character. Each of them contains a character. So each space H alpha in that case is finite dimensional. So this basis consists of only one function, and this function is a character. And then we recapture this formula somehow, because, if we put if we apply the operator ut to a character, then we obtain simply x he of x plus t. I use here probably I can use the multiplicative notation, only we must remember that this is commutative. So, and this is so there is only one coefficient here, and it's equal. This coefficient as a function is the same character as we have here. So how here everything is trivial and very, very simple. Now why this is so? Okay, so let H be one among the spaces H alpha. Let it be some space among the H alpha, and we consider our unitary operators, our shifts in the space H, and then let lambda of S be an eigenvalue of US on H. This is a finite dimensional space, some operator, it has some non-trivial eigenvalue. It is so a unitary operator must have a non-trivial eigenvalue, and consider the corresponding eigensubspace. Let H tilde be equal to the set of all H in H for which US H is equal to lambda S H. Слушаю. Да, да. 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 Понятно. Хорошо. А что будет вместо? Так, хорошо, а там еще в тот же день совет, оргкомитет Конгресса, он тоже отменяется или вот не знаю? Так, хорошо, ладно, буду звонить. Да, всего доброго. Так. Okay, so consider this subspace. Now apply to this relation another shift, ut, us, h is equal to lambda s, u, t, h. This is triviality. And now let's use the fact that our group is commutative, so we can interchange the order of these two operators. Well, and this means that h bar, h tilde, is also invariant under all right shifts. Well, but what does this mean? This means that our operator us well, okay, so this subspace is invariant. This subspace is invariant. Well, but our H was irreducible. So this means that this operator US is a multiple of the identity operator of the entire space H. So all functions in H satisfy this relation. They are stable under this shift. And what does this mean? This means that the space must be finely one-dimensional, because otherwise there are some other invariants of spaces. Well, and why? Okay, so this means that US is a multiple of identity. On H. Well, but the same argument applies to every other UT. So all UTs are multiples of identity on this space. Each operator UT is a multiple of identity. And then it follows that H must be one-dimensional, because otherwise it would contain some non-trivial invariants of space. So H is one-dimensional. And okay, let's write this relation once again. So we have now for every S in G and every F in H, we have F from Ts is equal to lambda of S F of T. Now put here T equal to the unit element of the group G. then we obtain Fs is equal to lambda of S, f of E, and this means that f itself, that the function lambda itself, lambda as a function of S, it belongs to the same space S, because it is a multiple of any f. Well, and now again, we can use this relation with lambda in place of f to obtain lambda, this one, lambda of Ts is equal to lambda of S, lambda of T, and this means that lambda is a character. So we have recaptured what we already knew from the general theory, that L2 on a commutative group has an orthogonal basis of characters. Well, now this happens on a commutative group, and now fortunately we have retained this formula. What happens in the general case? Well, here we have this formula, and I remind you that in the commutative case, this formula reduces to something very simple. Simply, this space is one-dimensional. This basis consists of only one function, and this thing is reduced to the following: ut chi is equal to key of t key. So this sum simply reduces to one term, and what is interesting that here this term as a function of t also belongs to the same space generated by chi. Okay, so somehow the coefficient of this decomposition also has something to do with the space H alpha. Yes. In the general case, this is not quite so. Things are more complicated, are more involved, but still there is some similarity, and I want to at least to make several steps towards what happens. Maybe I will not prove the most general the fact which is known here, but still, let's look more carefully at this decomposition, and okay, let's look at the coefficients. So what we our object of interest now. Our object of interest. So these are. Слушаю. Да. Да. Отменили. Понятно, да. Понятно. Да, мне уже сообщили по поводу заседания Совета по мат-центрам, то же самое в тот же день. Да. Хорошо. Теперь про какой-то перенос ничего не известно, да? Ну, понятно. То есть Конгресс-то терпит, а мат-центр-то не терпит, потому что деньги тратить не можем. Все то совещание. Да ладно. Хорошо, спасибо большое. Да, до свидания. So our object of interest is the coefficients in this decomposition. The functions well, probably it is reasonable to put the index alpha also here, because these coefficients depend also on the space, on the particular space in the decomposition. C G K alpha of T on G if G is not necessarily commutative. Is not necessarily commutative. We know that the characters are mutually orthogonal on the in the case of a compact group, but now what we want to do first is to prove some orthogonality relations between these functions. It will turn out that as a function of t, they are orthogonal within one value of alpha. And for different values of alpha, they are orthogonal if the dimensions of the corresponding spaces H alpha are different. If they are not different, this is not true, but we'll see anyway. Now, to see this, we need the lemma. We need a lemma which is due to Schur. We consider two representations. Of some group two respectively the group of maybe unitary, but it is not very important. They may be simple invertible unitary matrices of size R cross R and of size S crossed S. So this is a representation by matrices on a linear space of dimension S, and this is a representation by matrices of the linear span of dimension R. Here, even it is not required, in fact, to suppose that all matrices are unitary. they're invertible in any case because of this property of representation, phi of if we put here t equal to s to the power minus 1, we see that one of these operators are mutually invertible. So all values of any representations are always invertible, and here the fact that they are unitary is not important. Okay. So suppose there are two representations, and suppose they are intertwined by some operator. That is dTA is equal to ACT for all T in our group G. What is A? Here here we have matrices of size R, and here matrices of size T. So when we apply of size S, when we apply this matrix, we obtain a vector of size S, and then we must apply an operator, and we should obtain some vector of size R. So A acts from the complex Euclidean space of dimension S to the complex Euclidean space of dimension R. Okay? Then the conclusion is as follows. Then either A is equal to 0 or I is equal to S, and A is non-singular. I forgot to say that they are not simple representations, but irreducible representations. Suppose they are irreducible representations of some group by matrices of size R and matrices of size S. Then every operator that intertwines them must be either 0 or non-singular, and square, and then I is equal to S. Probably not to have many similar letters, it is useful to denote this Euclidean space by E and this by F. So A acts from E to F, and intertwines two irreducible representations. Okay. So proof. Consider the image. The image of A. So this is the space of F. Now let's show that it is invariant under dt. dt of v is equal to dt a e. It is equal to a c t e. Ct surely this is included in A E because Ct acts in E. Ct acts in E. Ct is here of size R. Well, Ct of size S, yes. Well, and this is V. So V is invariant under all dt, and we have assumed that this representation is irreducible. So either V is equal to 0 or V is equal to F. Okay, when V is equal to 0, we come across the first case. Then A is equal to 0, and that's all. When V is equal to F, that is A is on 2. We show that the kernel of A0, consider N equal to the kernel of A, then surely this N is not equal to E, because A is non-zero. A is on 2, so it is non-zero. N is not equal to E, but also we shall show that N is invariant. So suppose X is in N, then consider CTX and apply A to this. This is equal to dt AX, and this is equal to 0 because A of X is equal to 0. That is Ct of N is included in N. And hence we see that this N is an invariant subspace for this representation Ct, and it is not equal to E. And since Ct is irreducible, then we also have that. We also see that N is not equal to so it is a proper subspace, not equal to N. So the only possibility is that N is equal to 0, because this thing is irreducible. So, well, okay, we have proved our lemma, because this means that A is on 2 and has a trivial kernel, so that it is non-singular, and this may happen only when the dimensions coincide. Now, what does this mean for these coefficients? Consider two alpha here. Two different subspaces that called star. Two different subspaces occurring in this decomposition. Let C be a matrix. Also we denote by U alpha T the restriction of U T to H alpha, and of course the same with the index beta. So consider these two partial representations. They act in these spaces. We write the following integral. I'll explain what is this. The integral over G. Here we put some matrix C, and here we put U T beta, and here U alpha T to the power minus 1 dt. Okay. Here C is some matrix of proper size. That is, the spaces H alpha and H beta may have the same dimension and may have different dimensions. Anyway, when we apply this element to something, we are in the space H beta. So to this element we should be able to apply the separator C, and then we must be after this implication in H alpha, so that C is an arbitrary operator acting from H beta to H alpha, and so the size of C is measured accordingly. So let's write this formula, and let's denote this guy by A. C will be an arbitrary operator acting from H beta to H alpha, and we shall write it, of course, in terms of some matrix in this basis of these spaces. So we average this operator against these two representations and obtain some other operator A, which also acts from H beta to H alpha. So we claim that A intertwines ut alpha, ut beta, and ut alpha. Let's calculate this. Well, ut alpha a is equal to the integral over g of ut alpha, and here it is good to rename the integration, the variable of integration, because now t is something fixed. So u s to the power minus 1 alpha c ut beta. Well, and then we use the invariance of our measure. This is ut s to the power minus 1. Sorry, here it is S, sure. And now, so the integration is in S, not in T. Now I denote this by another letter. Let sigma, not sigma probably v be equal to t s to the power minus 1. Then s is equal to t v to the power minus 1. No, v to the power minus 1, sorry, v to the power minus 1t. The integral, well, probably it would be better to write this way. Then no. Well, this, so s v to the power minus s is equal to vt. The integral over g u alpha v to the power minus 1 c u beta vt over v this time. And here again, using this representation, we see that this is equal to a u beta c. So really our operator intertwines our two representations, and thus either this operator is equal to 0 or it is non-singular. So there are two cases. The first case is when the dimensions are different. The dimensions of these two spaces are different. So in this case, by the Schur lemma which I raised, the matrix A must be equal to 0, because it cannot be non-singular. if the dimensions are different. Now what? Now we take this C, so that C G0 K0 is equal to 1, and otherwise the coefficients Cjk are 0. So take an elementary matrix C. And what do we have? We have that if we integrate this thing with this matrix C, we obtain 0. But when we apply here this matrix C, we obtain something very simple, because only one element of C is not equal to 0. So the thing that we apply is that we obtain is the following. Simply from this it remains only the following term. Only one term remains. So this is equal to 0, but not x, sorry, it's C, not x but C. You should not mix up this C coefficients of this decomposition with the coefficients of this matrix. So when I consider this decomposition, I put an upper index which is related to the space in question. So we have this, and this we can replace by C G0 K of T beta bar, because these things are the coefficients of a unitary matrix, and this matrix, when we replace T by T to the power minus 1 and replace to the inverse matrix, and the inverse matrix to a unitary matrix is calculated in the following way. So we precisely obtain that these coefficients as functions of T are orthogonal if we consider elementary irreducible subspaces of different dimensions. As to the case of equal dimensions, this we will analyze the next time. Okay, thank you.